Hey guys, I'm Prathamesh and I'll be talking about quantum computation with graphene. Graphene is the first truly two-dimensional condensed matter system discovered experimentally in the group of kind at the University of Manchester in 2004, which also won him the Nobel Prize. Its low energy dynamics of electrons is governed by states near two inequivalent K points in the Brillouin zone, which makes it such a great material to work with. Here in this presentation, we'll be dealing with graphene quantum dots. Quantum dots are tiny islands of electrons, where charging effects as well as quantum confinement play a crucial role. Quantum dots have been proposed as a host for a quantum bit, where the spin of an electron residing in a quantum dot forms the fundamental two-level subsystem of a qubit. Arrays of such quantum dots with tunable tunnel couplings between them would then work as a universal quantum computer. Decoherence can be viewed as a loss of information from the system into the environment, since every system is loosely coupled with the energetic state of its surrounding. Viewed in isolation, the system's dynamics are non-unitary, although the combined system plus environment evolves in a unitary fashion. As with any coupling, entanglements are generated between the system and the environment. These have the effect of sharing quantum information with or transferring it to the surroundings. Decoherence represents a challenge for practical realization of quantum computers, since such machines are expected to rely heavily on the undisturbed evolution of quantum coherences. They require that quantum states be preserved and that decoherence is managed in order to actually perform quantum computation. Electron spin is a very promising candidate for solid-state qubit. Major experimental breakthroughs have been achieved in recent years using quantum dots formed in semiconductor heterostructures based on gallium arsenide technology. In such devices, the major sources of spin decoherences have been identified as the spin-orbit interaction, coupling the spin to lattice vibrations, and the hyperfine interaction of the electron spin with the surrounding nuclear spins. There are many ways in which one could try suppressing decoherence of the system. Dephasing due to 1 by f noise and other slow fluctuations in the qubit's environment can be reduced by the so-called quantum backband control, when a series of pi pulse flips periodically cancel the random qubit phase. We could also try to employ a scheme involving a transpon, a type of superconducting charge qubit that was designed to have reduced sensitivity to charge noise. The transpon achieves its reduced sensitivity to charge noise by significantly increasing the ratio of the Josephson energy to the charging energy. This is accomplished through the use of a large shunting capacitor. We could enhance or suppress the relaxation rate of a qubit by tuning the qubit in and out of resonance with the prevalent noise source. Or we could try removing sources of decoherence by exploring better materials like graphene, which is the focus of this presentation. It is desirable to form qubits in quantum dots based on materials where spin-orbit coupling and hyperfine interaction are considerably weaker. It is well known that carbon-based materials such as nanotubes or graphene are excellent candidates for this purpose. This is because spin-orbit coupling is weak in graphene owing to its relatively low atomic weight, and because natural carbon consists predominantly of zero-spin isotope C12, for which the hyperfine interaction is absent. Spin qubits in graphene can not only be coupled between nearest neighbor quantum dots, but also over long distances, thus making the system ideal for fault-tolerance quantum computation and hence for scalability. It offers a low rate due to weak decoherences, which is a low rate for errors, in combination with a high error threshold due to the possibility of long-range coupling. A fundamental problem needs to be overcome before graphene can be used to form spin qubits. It is difficult to create a tunable quantum dot in graphene because of the absence of a gap in its energy spectrum. The phenomenon of Klein tunneling makes it hard to confine particles. When graphene is patterned into a narrow ribbon and the carriers are confined to a quasi one-dimensional system, we can see the opening of an energy gap. Similar to carbon nanotubes, this energy gap depends on the width and crystallographic orientation of the graphene nanoribbon, as shown in these figures. The figure on this left represents schematic energy band diagram with a bias voltage applied and the conductances of three devices with different widths of nanoribbons. The figure on this right represents overall scaling of the energy gap for six different devices as a function of their widths. Similarly for electrons, they can be confined by using suitable transfer states in a ribbon of graphene. Let us see the bound state solutions in this setup, which are required for a localized qubit. A single quantum dot is assumed to be rectangular with width W and length L. Basic idea of forming the dot is to take a ribbon of graphene with semiconducting armchair boundary conditions in the x direction and to electrically confine the particles in the y direction. The low energy properties of electrons in such a setup are described by this Dirac equation, where this potential is the gate voltage in the dot region and the barrier voltage in the barrier regions. Making the wave function continuous at the boundaries, we get the quantization condition for wave vector in x direction, which is inversely proportional to the width of nanoribbon. This determines the energy gap for excitations, which is of the order of 60 millielectron volt, which is unusually small for semiconductors. This is a unique feature of graphene that will allow for long-distance coupling of spin qubits. A transcendental equation for energy with wave function matching at the ends of the ribbon is obtained as this. A detailed derivation can be found in this paper, but what's important is that the bound state solutions obtained from this equation for two different dot sizes differ, as they should in theory. Here are the energy bands for two barriers and a single dot. The red area marks a continuum of states in the valence bands and the blue area marks a continuum of energy states in the conduction band. In the barrier regions, it is indicated that the energy bands of the quantized modes are due to transverse confinement. All modes are non-degenerate solutions in Wally space. In the dot region, the electric confinement in the longitudinal direction yields an additional level structure. Similarly, for a double dot setup, a single bound state is shown in the conduction band of the left dot and two bound states are shown in the conduction band of the right dot. They are coupled via the continuum in the valence band of the central barrier. Long-distance coupling of three graphene qubits can be seen here. The energy bands of three quantum dots, including the barrier regions, are shown in which dot 1 and dot 3 are strongly coupled via co-tunneling processes through the valence bands of barrier 2, barrier 3, and dot 2. Moreover, the center dot 2 can be decoupled by detuning. The energy levels can be chosen such that delta epsilon 2 is less than delta epsilon 1. The qubit piano illustrates many qubits in a line hosted within a graphene nanoribbon. Quantum dots are red bars and barrier regions are blue bars. Different spin qubits that are strongly coupled to each other via Klein tunneling are marked with the same color. Now we know that electrostatic confinement of massless charge carriers is hampered by Klein tunneling. Circumventing this problem in graphene mainly relies on carving out nanostructures or applying electric displacement fields to open a band gap in bilayer graphene. So far, these approaches suffer from edge disorder or insufficiently controlled localization of electrons. An alternative strategy in monolayer graphene, by combining a homogeneous magnetic field and electrostatic confinement, can be implemented by using the tip of a scanning tunneling microscope to induce a confining potential in the Landau gaps of bulk graphene without the need of physical edges. The demonstrated confinement approach appears suitable to create quantum dots with well-defined wave function properties beyond the reach of traditional techniques. We also have read a lot about nitrogen vacancy centers in diamonds that could be used to construct vital components of quantum computers. But it has been very difficult to read optically written information for such systems electronically. Researchers have built a technique based on direct transfer of energy from nitrogen vacancy centers in nanodiamonds to a directly neighboring graphene layer. When laser light shines on a nanodiamond, a photon raises an electron from its ground state to an excited state in the nitrogen vacancy center. The system of the excited electron and the vacated ground state can be viewed as a dipole. This dipole in turn induces another dipole comprising of an electron and a vacancy in the neighboring graphene layer. Alright, so in conclusion, graphene, as we have seen, has great potential for an ideal candidate for spin qubits due to its low intrinsic spin qubit coupling and sparse amount of nuclear spins. For future work, bilayer graphene can be potentially superior to single layer graphene due to the creation of tunable bandgap by electric fields which allow for an all-electric control of graphene quantum dots. Thank you.